But if it's finite, if alpha is finite, and that means finitely many points, finitely many lines, then this arc implies pathos. So associativity of the ring with the division will imply commutativity. And this is purely beautiful algebraic fact, which first Wedderburn, and I think it's 1905 somewhere, he did it, and
that's a famous Wedderburn theorem.
Oh yeah, that's famous, that if you have finite ring with the division, it must be commutative.
But the motivation was
absolutely right. The point is that when you start doing, when you try to answer this question and you look at what theorems can happen, that really became the source of the strangest algebraic systems, like semi-field, quasi-fields. You have distributive law on one side, you don't have on another side. Later it all was revisited by Marshall Hall, and he came with notion of ternary rings. And all those objects, it's very, really broad concept. It's on the level of functions. And then particular cases of those ternary rings became all this strangest. So it appeared natural. That's, what was.
But later on it became very artificial.
That's right. When people forget, the source, they hear about semi-field or quasi-field, they wonder why. It's, of course, there are stories. Wedderburn published a paper when he gave 3 proofs of this result. And really, he later generalizes to Artin Wedderburn for associative algebras, over R, finitely dimensional, which have division. You just got beautiful theory there. It's characterization of semi-simple algebras. But in this paper, he had 3 proofs. And he acknowledged that the second 2 proofs really that he read, paper of Dixon, who also independently, almost the same time, did it. And then Paschal, when he wrote on history of this theorem, he actually understood that there was a big gap in the first proof of Wedderburn, but the second and the third were fine. But the second and the first was after he read the Dixon. But Dixon's proof was before the second and the third. So it should be called theorem of Dixon, Wedderburn at least, because that was the first, historical. So that's how it went. And that's, this beautiful theorem relates to these 2 facts. All right. If I write here, it won't be convenient, right? What about you, Laura? You can see it here. Then I will use this. So we were talking only about finite. So now about finiteness. Okay. The third axiom gives you 3 points, and it's A, B, C. What about other points? And of course, this line must be there, this line, and this line must be there. That's the third axiom. Now, there must be lines through C parallel to AB. You must have. There must be lines through A parallel to BC, and it will be new line if it's parallel. Parallel means don't intersect. Then, you can argue that these 2 lines must intersect, and you will get the 4th point D. Now you have these lines. You need line DB, because in affine plane, every 2 distinct points define a line. So now you got 4 points, and you got 6 lines. And you can easily check that this set theoretic construction, A, B, C, D, set of points, and set of lines will be just AB, BC, and so forth, CD, 6 lines, it's like this system of subsets, and you can easily check that all three axioms meet. So it's like hypergraph, two uniform hypergraph on a set of ABCD. So it's completely new view of all that as design or hypergraph. So the question is, all right, what about 5 points? Can we do it on 6 points? So, and most of you, I'm sure, have seen it that if you can do it on n points, if alpha is finite, then then cardinality of the set of points, which is sometimes cardinality of alpha, I can write P of alpha, must be n squared. It's necessarily n squared. And number of lines will be necessarily n squared plus n. And it exhibits necessarily a lot of symmetry, that there will be exactly n points on every line, and there will be exactly n plus 1 line through every point. So it's completely very symmetric stuff. Very symmetric stuff. Now, for which n you can really build it? For n equals q equals p to the e prime power, you can build it. And the way you build it, just take in a field of q elements, finite field, and it was null, and then you create such a field. So from combinatorial point of view, it seems very, very hard thing to build it by hand. And here with this simple idea and finite field, we do it. So of course, we indept the existence of finite field, which are unbelievable combinatorial structures, especially if it's not prime number of element, but prime power number of element. They are, the most rich combinatorial structure maybe you can think about. In what sense, of course, it's not really. All right, so that's why it's easy for that. What about other n? And that's what makes, everyone love this subject. No one knows. No one knows example of a affine plane. It's called order n, of course, in this case. It's called order n. No one knows any example when n is not prime power.
So it's analogous to projective planes?
It's absolutely analogous. It's very close to all questions about projective planes. So no one knows that. Just affine planes, a little bit simpler, I think, to talk about, but that's it. So if n is p prime, these ones, which we call AG2 FP, finite field of p element, are the only known. Are only known. So another big question is, are they unique? Or if you take, order P affine plane, P will be number of points per line. If you take order P, are there any others? No one knows that. So you see, this question appeared at the beginning of 20th century, and no one can answer it. That's what is beauty. And so this is not known. And what if, what about these?
So is there a conjecture?
No, for this prime power, they are known. And what you take will be precisely AG to FQ. So when you take finite field of Q element,
Yeah, but for other n.
for other n, it's conjecture.
Do you have a feeling what answer?
I don't. I didn't work that much on it. It's just no one can imagine how, because people tried it so hard so far. But you see, there are interesting things that if this was unique, then there would not be a big question. But if n equals p to the e and e is at least 2, there are many. There are many affine planes. If, for example, the smallest example here would be n equals 9, where you have more than one. And for n equals 9, Veblen constructed 5 planes. 5 planes. for n equals 25, that's 5 squared. For 16, you have about 17 planes. For order 25, you have 194, I think. No one knows precisely how many, but that's at least, I have the number. Yeah, 194.
Is there an upper bound?
Yeah, but it's very, very just stupid. Yeah. This work is still Eric Morehouse from the University of Wyoming. Yeah.
So let me just understand.
Yeah.
So it's known that this number of points has to be a square, and the only known ones are prime powers. So the question is whether there is one that's a square but not a prime power?
Yeah, and prime power it's n, you know, and this is n squared. So n is the parameter which is number of points on the line.
But some special cases are known, right? 6.
In some small cases it's known, and absolutely right.
But for the projective case, famously, projective plane of order 10.
The same, I'll mention it right now.
Yeah.
I'll mention it. Now, for n equals 49, already you have 309,000. There are so many, and it's expected that it's at least 500,000. Again, that's Eric Morehouse. His computer's working non-stop.
But are they equivalent in some sense?
No. You see, that's the point. They are distinct. Distinct in what sense, of course? Which two projective planes you will call isomorphic? You will call them isomorphic if there is bijection between points, which induces bijection between lines, such that incidence is preserved. So that is the definition.
But to describe
So these
them,
are not isomorphic.
To describe them, you need to specifically, or you have some parameters?
Matrix, you can use 0-1 matrices, you can describe them.
But 390,000 distinct objects?
At
or
least
they
distinct,
have
not
parameters
isomorphic.
you can plug in?
No, they are not isomorphic objects. They have 49 square points.
You have to actually describe them one by one.
Oh yeah, yeah.
You cannot have families.
You can have families, translation planes, different types
No, I
of
mean,
planes.
what's the minimal number of data to describe them all? You need...
Not clear. You
Yeah.
see a huge absolute amount of things. So people expect that there are maybe 500,000, but it's work. All right. So now, what about other end? Of course, there are these big theorems. First of all, there is this big theorem, Bragg and Reiser 49. That's one of the most important results of non-exist. So it says that if alpha of order n exists, then n exists and n is 1, 2, mod 4. Mod 4. If there exists a fine plane of order n, and n is 1, 2, or 4, then n is a sum of two integer squares. Necessary. So this is really a beautiful theorem. It's not if and not. So that's the theorem. And of course it settles some non-existent cases. And the first one is 6. 6 is 2 mod 4, but 6 is not a sum of two squares. Another is 14. 14 is 2 mod 4, but 14 is not sum of two integer squares. On the other hand, none of them is prime power. On the other hand, n equals 10 and 12 don't fit this. 10 seems to be perfect. It's 2 mod 4, but 10 is this 3 squared plus 1 squared. So, so there is no contradiction. It may exist, but we know that it does not exist because of Lamb and others who used. For 12, the answer, as far as I know, is not known yet. It doesn't fit this n, of course. It doesn't fit this, but it's not known. So this is a great theorem, and that's one of the strongest results, you know, which imposes restrictions. So that is this. I have 5 minutes. At least, I hope that you can appreciate affine plane. Projective planes are easy. So what you do to get projective planes from affine, you do this. In affine plane, you have parallel lines. So you just pick a new point, you add new element to set of points, and you add it to every line from this. And if you have another set of parallel lines, you add another. Okay. So then you collect all these points in a set which is called line at infinity, and you get easily that all these old lines of affine plane, that's how you go from alpha to pi, projective plane. So one more line, and every line here extended by exactly 1 point. So that's how you get projective. And in projective plane, you have, of course, unique lines through 2 points. You have every line 2 intersects in 1, and there are 4 points, no 3 on 1 line. That's the essence of projective plane. And projective planes are more symmetrical, really. So people study projective because there is more symmetry. But if you take projective plane, erase any line and all points on it from the remaining lines, you will get affine plane. You won't get the same affine plane for every line you delete. You may get non-isomorphic affine planes, but it will be affine plane. On the other hand, completion of affine plane gives you unique projective plane. All right, so now closer to the result. So the question is, there is this notion of Levy graph of alpha or Levy graph of pi. That's a bipartite graph whose sets are points and lines. It's a bipartite graph such that this vertex P is joined to line L if P belongs to L. So for every affine plane or projective, you can build what's called Levy graph of that. It's always bipartite graph. Now, this graph has no C4. C4 is not a subgraph of Levy, of alpha, or of pi. The reason is simple. This graph is bipartite. It cannot have odd cycles, but it has only even cycles. And why it cannot have C4 is this. Because suppose it has C4, then it will look like that. But that means that these 2 points lie on this line, and the same 2 points lie on another line. And that cannot happen. So if you take Levy graph of affine or projective plane, it's C4-3. Okay, what can you find in these planes? Is necessarily 6 cycle there, yeah? 8 cycle, yes. But if you have, say, n squared points, or for projective plane, the total number of points is this. If you take so many points, and number of lines will be the same for projective plane. Do we have cycle of any permissible length? And that's what we were working recently with Mellinger and Gega. And it's published in the electronic journal. It took us 2 years to answer this question. Can you find really every even cycle of permissible lengths in these 2? Permissible, I mean, here it cannot be more than n squared points. And here it cannot be no more than that. In particular, are they Hamiltonian? You see, there was a classical result about Hamiltonicity of PG to Q. That's, projective plane which you have obtained from affine plane if you use field. Then it was a result of Singer of 1938 that it's Hamiltonian. Singer cycle. You might hear about this. It's absolutely beautiful object. But if you take just the projective plane of order Q, you don't know that. Not every plane looks like that. Projective plane or affine plane, not every affine plane looks like that. So it wasn't clear. So that's what we were working on, and unfortunately I don't have time to give you. There is a very simple basic idea to establish existence of certain cycle, and then you just glue them together. And it's published so one can see it. What is unknown is this. there are many unknown questions here, but the one I want just to pose is this. It's a nice theorem of Ostrom that whatever finite plane you have, you can find Desarguin configuration there. In every finite plane, there is at least one. Desarguin theorem doesn't have to hold unless plane is classical. So this Desarguin configuration is embedded, in every finite projective plane. You can embed the Desarguin configuration. It's not a theorem there, but you can find it. No one knows about Pappus. Whoever I ask, is it true that in every finite projective plane you can find Pappus configuration? It's not. Is it true that in every non-Desarguin plane you can find Fano? And Fano is PG22, so that's famous Fano.
Can you find at least one?
Yeah. In every non-Desarguin plane, IQ, you can find millions of them. There are so many of them. And there is a conjecture by Hanna Neumann that every non-Desarguin plane will contain this. You can rephrase it in a graph. If you take Levy graph of this, this is a very famous graph, Hewitt graph. So you can ask, whether given bipartite graph is a subgraph of projective plane. So can you find Hewitt in some project? Everyone believes it's true. No one can prove it. That Fano plane can be found. Fano plane cannot be found, in Desarguin plane. If this is not power of 2, for Desarguin plane, which are built over the field, you cannot do it. If it's like 3 element in the field, or 3 square, or 5 to the 10th, you can. It should be power of 2 for you to do it. That's, follows from this algebra. I'm over, and Dora has already been too patient. Thank you very much.
We get to answer questions.